Right now, you're riding a hidden carousel about 1,000 miles an hour at the equator, while Earth turns with a rhythm set in the solar system's first dawn. Imagine, for a breath, that the spin stops. The ground becomes still, but the air and oceans keep moving east, momentum unspooling into supersonic winds and basin-scale surges that redraw coasts before they calm. A year-long day begins, a blazing hemisphere under an unblinking sun, a frozen hemisphere facing the stars, and a twilight ring where temperatures stay almost gentle. In the deep, the geodynamo that shields us from charged particles would reorganize and likely weaken, not vanish at once. Proof that rotation quietly shapes our weather, our oceans, and even our magnetic sky. Tonight, we'll open this what-if carefully. The physics of inertia, the collapse of jet streams and gyres, the reshaping of tides and shorelines, and why a simple spin may be the most underappreciated life support system on Earth. Earth completes one rotation every 23 hours, 56 minutes, and 4 seconds relative to distant stars. This is called a sidereal day. A solar day, 24 hours, differs from the sidereal day because Earth advances in its orbit each turn, requiring slightly more rotation to face the Sun again. This 4-minute sidereal solar difference explains why stars shift in the night sky. Leap years, however, correct that the tropical year is approximately 365. 2,422 days, not exactly 365. At the equator, the surface moves at 1,670 kilometers per hour, faster than the speed of sound relative to Earth's axis, though this creates no sonic boom since the air co-rotates with the surface. This velocity decreases as you move toward the poles, following a mathematical relationship based on the cosine of latitude. At 45 degrees latitude, roughly the location of cities like Minneapolis or Turin, the rotational speed drops to about 1,180 kilometers per hour. At the Arctic Circle, it's approximately 670 kilometers per hour. At the poles themselves, the rotational speed is effectively zero. You would simply pivot in place as the planet turns beneath you. This rotation creates centrifugal force that causes Earth's equatorial bulge, making our planet an oblate spheroid rather than a perfect sphere. The difference is substantial. Earth's equatorial diameter is 12,756 kilometers, while the polar diameter is 12,714 kilometers, a difference of 42 kilometers. This bulge affects everything from satellite orbits to the precise measurement of gravity, which is about 0.5% weaker at the equator compared to the poles due to both the centrifugal effect and the greater distance from Earth's center. The rotational energy comes from angular momentum Earth gained during its formation 4.5 billion years ago. During the early solar system, countless collisions of planetesimals and debris gradually built up our planet while imparting rotational energy. The largest of these impacts likely involved a Mars-sized object that created our Moon. This collision also contributed significantly to Earth's final rotational rate and axial tilt of 23.5 degrees. This spin affects far more than our 24-hour day-night cycle. Earth's rotation drives the Coriolis effect, which curves the path of moving objects, including air masses and ocean currents. Without this effect, we wouldn't have the spiral structure of hurricanes, the circulation patterns of ocean gyres like the Gulf Stream, or the complex 3-cell atmospheric circulation system that distributes heat from the equator to the poles. The rotation also generates Earth's magnetic field through the geodynamo process, as conducting liquid iron in the outer core moves in organized patterns influenced by the planet's spin. Earth's rotation gradually slows due to tidal friction with the Moon at a rate of about 2.3 milliseconds per century. This happens because the Moon's gravity creates bulges in Earth's oceans, and as our planet rotates beneath these bulges, friction occurs. The energy lost from Earth's rotation gets transferred to the Moon's orbital energy, causing our satellite to slowly spiral outward at about 3.8 centimeters per year. Understanding Earth's current rotation provides the foundation for analyzing what would happen if this fundamental motion suddenly stopped. If Earth's rotation stopped instantly, The atmosphere and oceans would continue moving eastward at their current speeds due to inertia. Newton's first law of motion states that objects in motion tend to stay in motion unless acted upon by an external force. At the equator, this means air and water would keep moving at 1,670 kilometers per hour, while the solid surface becomes stationary. This creates a massive velocity differential between the planet's surface and its fluid layers. Imagine standing on a train platform while a freight train rushes past at highway speeds, except the train is the entire atmosphere and ocean system. The scale of this phenomenon defies everyday experience. The atmosphere contains approximately 5.15 times 10 to the power of 18 kilograms of air, while the oceans hold about 1.37 times 10 to the power of 21 kilograms of water. All of this mass would suddenly have a horizontal velocity relative to the ground ranging from 1,670 kilometers per hour at the equator to 0 at the poles. The kinetic energy stored in Earth's rotation is approximately 2.6 times 10 to the 29th joules, roughly equivalent to the energy released by 100 billion nuclear weapons or the total energy consumption of human civilization for 20,000 years. This enormous energy would be dissipated through multiple friction mechanisms. Air-surface interactions would create the most immediate and visible effects, as the atmosphere scrapes against mountains, buildings, forests, and terrain features. Every surface irregularity, from individual trees to mountain ranges, would act like sandpaper against the moving air. Ocean seafloor contact would generate friction through a different mechanism, as water flowing over the seabed creates turbulent boundary layers and bottom drag. Internal shear forces within the fluids themselves would also play a crucial role, as different layers of air and water moving at slightly different speeds would create viscous friction. The timescale for energy dissipation depends on the specific friction mechanism. Atmospheric friction with the surface would be most efficient near the ground, where air density is highest and surface contact most intense. The process would work like a massive brake system, with surface friction gradually slowing each layer of the atmosphere, which would then slow the layer above it through turbulent mixing. Ocean currents would take longer to dissipate due to water's higher density and the smoother interface between water and seafloor compared to air and land surfaces. Regional variations would be dramatic. At the equator, where relative velocities are highest, the friction would be most intense. Mountain ranges oriented north-south would experience the greatest stress, as they would present the largest cross-sectional area to the eastward moving air. The Andes Mountains, running roughly north-south along South America's western coast, would face winds like a massive wall. Conversely, east-west mountain ranges like the Himalayas would create enormous wind shadows on their eastern sides. The heat generated by this friction would be substantial but distributed over the entire planetary surface and atmosphere. Unlike a concentrated explosion, this energy release would occur gradually over weeks to months. The unprecedented wind speeds would gradually decrease following an exponential decay pattern, with initial velocities dropping from 1,670 kilometers per hour to perhaps 1,000 kilometers per hour within days, then 500 kilometers per hour within weeks. This initial phase would last several weeks to months before the fluid layers match the now stationary surface. With the surface suddenly motionless, near-equatorial winds would initially reach supersonic speeds, 1,500 to 1,700 kilometers per hour, then gradually weaken over months as friction transfers momentum to the ground. These velocities approach Mach 1.4 at sea level, creating shock waves and sonic booms across vast regions, though shock structures would be complex and terrain-dependent. The atmosphere would behave like a massive fluid flowing over a suddenly stationary landscape, generating phenomena never before witnessed in Earth's meteorological history. This dissipation would produce regional heating through several mechanisms. As supersonic air compresses against surface obstacles, it would heat dramatically, similar to how spacecraft experience heating during atmospheric re-entry, but occurring horizontally across continents. The mechanical friction between air and surface would convert kinetic energy directly to thermal energy. Calculations suggest that regions experiencing the most intense wind friction could see temperature increases of 10 to 30 degrees Celsius above normal, particularly in areas with rough terrain or dense vegetation. The interaction would generate vast dust and aerosol loads that could alter short-term radiative balance in complex ways. Desert regions like the Sahara, Gobi, and Australian outback would become sources of unprecedented dust storms, lofting billions of tons of particles into the atmosphere. These aerosols would scatter incoming solar radiation, potentially cooling some regions even as friction heats others. The competing effects of frictional heating and aerosol cooling would create a patchwork of temperature anomalies across the planet's surface. Mountain ranges would create massive wind shadows and turbulent zones with dramatic regional variations. The Rocky Mountains, running north-south across western North America, would face the full force of eastward moving air, creating extreme turbulence on their western slopes and relative calm in their eastern lee. The Himalayas, oriented east-west, would split the atmospheric flow, deflecting air masses northward and southward around their bulk. These interactions would generate standing waves, rotor clouds, and turbulence extending hundreds of kilometers downwind from major mountain barriers. The jet streams, which depend on Earth's rotation and the Coriolis effect, would completely disappear. Currently, these narrow bands of fast-moving air at altitudes of 9 to 16 kilometers help steer weather systems and maintain the meandering patterns that bring seasonal precipitation to many regions. Their absence would eliminate the familiar progression of high and low pressure systems that characterize mid-latitude weather. Storm tracks that currently follow jet stream patterns, bringing rain to California, snow to the northeastern United States, and seasonal monsoons to various regions, would cease to exist. The tremendous friction could cause significant regional heating, while dust and aerosols might also create short-term cooling in some regions, leading to a complex mosaic of climate effects. Coastal areas would experience unique conditions as land and sea surfaces respond differently to the atmospheric chaos. The normally stabilizing effect of large water bodies would be overwhelmed by the massive atmospheric momentum, creating unprecedented weather conditions that defy all existing meteorological models and forecasting systems. These atmospheric changes would set the stage for the fundamental reorganization of global air circulation patterns. Earth's oceans contain approximately 1.37 billion cubic kilometers of water, with an average depth of 3,688 meters, covering 71% of the planet's surface. While the bulk ocean doesn't move as a rigid shell at 1,670 kilometers per hour, the relative motion between water and the suddenly stationary crust would drive basin-scale surges and transient coastal mega-flooding of extraordinary height, with magnitudes set by basin geometry and seafloor shape. The ocean's response would be far more complex than the atmosphere due to water's thousand-fold greater density and the confining effects of basin topography. The initial oceanic response would vary dramatically by basin geometry and latitude. In the Pacific Ocean, the world's largest water body, the eastward momentum would drive massive surges against the western coasts of North and South America. The Pacific's great width, roughly 19,000 kilometers at the equator, means that billions of cubic kilometers of water would pile up against these coastlines. Coastal cities from Seattle to Santiago would face walls of water fundamentally different from tsunami waves, because this water would maintain its eastward momentum for months rather than oscillating back and forth. The Atlantic Ocean, narrower but still vast, would similarly drive water against European and African coastlines. The Mediterranean Sea, essentially a large enclosed basin, would experience complex sloshing patterns as water momentum interacts with the basin's irregular boundaries. Shallow seas like the North Sea and Baltic Sea would experience the most dramatic relative changes, as their limited depth provides less volume to absorb the horizontal momentum. The kinetic energy of the moving oceans would be gradually dissipated through friction with the seafloor and coastlines over several months. Unlike atmospheric friction, which occurs primarily at the surface, oceanic friction operates through different mechanisms. Bottom friction affects the entire water column through turbulent mixing, while coastal friction creates complex eddy systems and upwelling zones. The deep ocean, with its smoother seafloor topography, would retain momentum longer than shallow coastal seas with their irregular bathymetry and tidal flats. Ocean currents driven by the Coriolis effect would cease to exist, eliminating some of Earth's most important heat transport systems. The Gulf Stream, which carries 30 sverdrups, 30 million cubic meters per second, of warm water northward along North America's east coast, would halt within weeks. This current system transports roughly 1.4 petawatts of heat, equivalent to 100 times global energy consumption, from tropical to temperate regions. Its disappearance would fundamentally alter the climate of northwestern Europe. The Kuroshio Current, the Pacific's equivalent to the Gulf Stream, carries warm water past Japan and into the North Pacific. The Antarctic Circumpolar Current, the world's largest current system at 600 sverdrups, would collapse without westerlies to drive it. This current connects all three major ocean basins and plays a crucial role in global heat distribution and carbon cycling. Its absence would isolate Antarctica's waters and disrupt the global thermohaline circulation system. The timeline for these circulation changes would vary by depth and location. Surface currents would adjust within months to years as wind patterns change and thermal gradients establish. Deep water circulation, which currently takes centuries to millennia for complete circulation cycles, would reorganize over decades to centuries as the ocean's circulation engine rebuilds itself. With rotation stopped relative to the stars, one side of Earth would face the Sun permanently, while the other faces away. However, Earth would still orbit the Sun, so the day side would slowly shift over the course of a year. This fundamental change transforms our understanding of day and night from a 24-hour cycle to a 365.2 5-day cycle, creating a solar day equal to 1 Earth year. The planet would still maintain its 23.5-degree axial tilt, adding seasonal complexity to this already dramatic restructuring of Earth's illumination patterns. The subsolar point, where the Sun appears directly overhead, would move slowly westward, taking an entire year to complete one circuit around the planet. This point would trace a figure 8 pattern called an analemma, due to Earth's elliptical orbit and axial tilt, just as it does currently. But this pattern would now be stretched across the entire year instead of being compressed into each day. The subsolar point would move approximately 0.986 degrees westward per day, 360 degrees divided by 365.25 days, roughly equivalent to 110 kilometers at the equator. Areas would experience approximately 6 months of continuous daylight, followed by 6 months of darkness. But this description oversimplifies the actual illumination patterns. The duration of light and dark periods would vary significantly with latitude. Equatorial regions would indeed experience roughly equal periods of daylight and darkness, as the subsolar point passes overhead and then moves to the opposite side of the planet. However, polar regions would experience more complex patterns due to the planet's axial tilt. During the equivalent of current summer months for each hemisphere, that hemisphere's polar region would experience extended daylight periods longer than 6 months, while during winter months, it would face extended darkness exceeding 6 months. This creates an extreme version of the polar day and polar night phenomena currently experienced at high latitudes, but extended across vast regions rather than being confined to areas within the Arctic and Antarctic circles. The transition zones between permanent day and night, often called terminator zones or twilight regions, would have the most stable temperatures and could become the primary habitable regions. These zones would experience a perpetual dawn or dusk condition, with the sun remaining near the horizon. The width of these transition zones would depend on atmospheric effects, particularly the scattering of sunlight through the atmosphere and the planet's topography. Mountain ranges could significantly affect local illumination patterns, creating complex shadows and reflected light zones. Within the terminator zones, the angle of sunlight would change gradually over the course of the year, as Earth's axial tilt causes seasonal variations. During the equivalent of summer for a particular hemisphere, the terminator zone on that hemisphere would receive more direct sunlight, while during winter it would receive more oblique illumination. This would create a form of seasonal variation even within these transition regions. The absence of Earth's rotation would eliminate several familiar phenomena related to the sun's apparent movement. Sunrise and sunset as discrete daily events would cease to exist for most of the planet. Only locations within the narrow terminator zones would experience something resembling these transitions, but stretched over months rather than minutes. Time measurement would become fundamentally different, making standardized time zones nearly meaningless, as local solar time would vary continuously and slowly. The permanent day side would experience continuous solar input without nighttime cooling, creating temperature conditions unprecedented in Earth's climate history. Local extremes near the subsolar region could approach the boiling point under specific conditions. Most dayside land likely stabilizes around 40 to 70 degrees Celsius, moderated by atmospheric circulation, cloud formation, and surface characteristics. However, particularly in desert areas with low humidity, minimal cloud cover, and dark surface materials that efficiently absorb solar radiation, some locations could reach more extreme temperatures. The heating process would follow predictable physical principles. Solar irradiance at Earth's distance from the Sun delivers approximately 1,361 watts per square meter at the top of the atmosphere. Under continuous illumination, surface temperatures would rise until thermal equilibrium is achieved, when outgoing infrared radiation balances incoming solar energy. In current desert regions like Death Valley or the Sahara, where daytime temperatures already exceed 50 degrees Celsius with only partial daily heating, continuous solar input could drive temperatures significantly higher. Geographic factors would create substantial temperature variations across the day side. Coastal areas would experience moderation from nearby oceans, which have enormous thermal capacity and would absorb heat, while circulating cooler water from deeper layers. Mountain regions would see complex temperature patterns, with high-altitude areas remaining cooler due to reduced atmospheric pressure and enhanced radiative cooling, while valleys could become extreme heat traps. Urban areas with extensive concrete and asphalt would likely experience severe heat island effects, potentially reaching the highest temperatures on the day side. The night side, by contrast, would cool toward -40 to -80 degrees Celsius or lower, especially inland areas far from oceanic thermal buffering. Without solar input, surfaces would radiate heat to space at approximately 390 watts per square meter, following the Stefan Boltzmann law at Earth's average temperature, but receive no replacement energy. The cooling rate would depend on atmospheric composition, cloud cover, and thermal conductivity of surface materials. Areas with high thermal mass, such as rocky terrain, or areas with substantial groundwater, would cool more slowly than sandy deserts or frozen surfaces. The most extreme temperatures would occur at the subsolar point, hottest, and the antisolar point, coldest. The subsolar point, where the Sun appears directly overhead, would receive maximum solar irradiance throughout the year. The antisolar point, located on the exact opposite side of Earth, would experience the longest duration without any solar input and would likely become the planet's coldest location. These points would migrate slowly as Earth orbits the Sun, creating moving zones of extreme temperature. Clouds and atmospheric heat transport would limit the most severe extremes through several mechanisms. On the day side, intense heating would drive strong convection, creating towering cumulonimbus clouds that reflect incoming solar radiation and provide some cooling through evaporation and precipitation. The global circulation system, with air rising on the day side and descending on the night side, would transport heat across the terminator boundary. The terminator zone would have the most moderate temperatures, potentially ranging from 0 degrees Celsius to 30 degrees Celsius, making it the most habitable region for existing Earth life. Seasonal variations would still exist due to Earth's axial tilt and elliptical orbit, creating complex thermal gradients that would shift gradually over the course of each year. Earth's magnetic field is generated by the motion of liquid iron in the outer core, driven by convection and influenced by the planet's rotation through a complex process called the geodynamo. This dynamo operates at depths of 2,900 to 5,150 kilometers below the surface, where temperatures exceed 4,000 degrees Celsius and pressures reach 135 to 360 gigapascals. Convection depends on heat flux from the inner core and compositional buoyancy as lighter elements separate from the iron-nickel alloy. Loss of rotation would fundamentally reorganize this dynamo and likely weaken the field on centennial to millennial scales. The current magnetic field strength averages about 50 microteslas at Earth's surface, varying from roughly 25 microteslas near the equator to 65 microteslas near the poles. This field extends far into space, creating the magnetosphere that deflects most solar wind particles and cosmic radiation. The dynamo process requires specific conditions: sufficient heat to drive convection, conducting fluid, liquid iron, and most crucially, the Coriolis forces created by planetary rotation that organize random convective motions into coherent flow patterns. Rotation's role in the geodynamo cannot be overstated. The Coriolis effect constrains convective flows in the outer core into helical columns aligned with the rotation axis. These columns, typically a few kilometers in diameter and extending through the entire outer core, generate electric currents that produce and maintain the magnetic field. Without rotation, these organized structures would collapse into chaotic convection patterns similar to those in a pot of boiling water, dramatically reducing the dynamo's efficiency. The magnetic field might weaken over hundreds to thousands of years as the convection patterns in the core reorganize without rotational constraints. Computer simulations suggest the field could weaken to 10 to 20% of its current strength, though it would likely not disappear entirely. Inner core inertia may sustain partial dynamo organization for some time, but without rotation's Coriolis constraints, long-term field strength and stability decline. Heat flux from the inner core would continue driving some convection, potentially maintaining a weak fluctuating magnetic field with frequent polarity reversals and complex multipole structures rather than the current stable dipole configuration. A weaker magnetic field would provide dramatically less protection from solar wind and cosmic radiation. The solar wind, a stream of charged particles traveling at 400 to 800 kilometers per second, currently deflects around Earth's magnetosphere. With a weakened field, this deflection would be less effective, allowing more particles to reach the upper atmosphere. The magnetosphere would shrink from its current size, extending roughly 60,000 kilometers on the day side and 600,000 kilometers in the tail, to perhaps 1/10 of these dimensions. This reduced protection would potentially lead to increased atmospheric loss over geological timescales through several mechanisms. Enhanced particle bombardment would heat the upper atmosphere, increasing the escape velocity for light gases like hydrogen and helium. Sputtering, where high-energy particles knock atmospheric molecules into space, would accelerate. Over millions of years, Earth could lose a significant fraction of its atmosphere, following a path similar to Mars. The aurora phenomena, currently concentrated near the magnetic poles where field lines converge and funnel particles into the atmosphere, would undergo dramatic changes, potentially spreading to different latitudes, becoming more diffuse and unpredictable, or covering much larger areas of the sky as the weakened field provides less organized particle guidance. Without the Coriolis effect, Earth's weather systems would be fundamentally different from anything in the planet's meteorological history. The Coriolis effect, that gentle spiral force that gives hurricanes their spin and shapes the flow of rivers, would vanish like a forgotten song. Weather patterns that have sculpted climate for millions of years would suddenly lose their rhythm. Storm systems would collapse or transform into strange, linear formations that move in straight lines across continents rather than the familiar spiral patterns we recognize today. Hurricanes and cyclones, which depend on rotational dynamics for their characteristic spiral structure and intense circulation, could not form in their current patterns. These massive storm systems derive their power from the organization that rotation provides. As air rushes toward a low-pressure center, the Coriolis effect deflects it, creating the spinning motion that allows these storms to intensify and maintain their structure. Without this deflection, air would flow directly toward low-pressure areas and fill them quickly, preventing the development of organized storm systems. Instead, weather would be dominated by direct convection between the hot day side and cold night side. Air would rise on the day side, flow toward the night side at high altitude, descend on the night side, and return to the day side at low altitude, creating a simple two-cell circulation system that would replace Earth's current complex three-cell structure in each hemisphere. This simplified circulation would be far more predictable, but also more extreme. Expect a permanent subsolar convective hub with deep thunderstorms where the sun's heating is most intense, and night-side radiative cooling with broad subsidence creating high-pressure zones on the permanently dark hemisphere. The trade winds, which currently blow from northeast to southwest in the northern hemisphere and southeast to northwest in the southern hemisphere due to Coriolis effects, would be replaced by direct east-to-west flow from night to day side. This would result in constant strong winds blowing from the night side toward the day side, a permanent atmospheric river transporting cooler air toward the heated regions and warm air back toward the cooling regions. The absence of jet streams would eliminate many current weather patterns, making climate more predictable but also more extreme. Jet streams currently create the meandering patterns that bring seasonal precipitation to many regions, steer storm tracks, and create the complex interplay between high and low pressure systems that characterizes mid-latitude weather. Without these steering currents, the familiar progression of weather fronts would disappear. The intertropical convergence zone, where northeast and southeast trade winds currently meet and create the world's largest rainforest systems, would reorganize into a linear convergence zone along the day-night boundary. This new convergence zone would become a permanent feature of the planet's climate, creating intense precipitation where the day-side and night-side air masses meet. Temperature contrasts between the hemispheres would drive this circulation with unprecedented intensity, creating wind speeds that could reach several hundred kilometers per hour as the atmosphere continuously works to balance the extreme temperature differences between permanent day and night. Earth's current oblate shape, flattened at poles, bulged at equator, is maintained by centrifugal force from rotation, creating a planet that is 78 kilometers wider at the equator than from pole to pole. The equatorial radius measures 6,378.137 kilometers, while the polar radius is 6,356.752 kilometers, resulting in a flattening ratio of approximately 1:298. Without rotation, gravity would gradually reshape the planet into a perfect sphere over thousands to millions of years, fundamentally altering the planet's geography and gravitational field. This transformation represents one of the most significant geological processes imaginable. The current equatorial bulge contains an enormous amount of excess mass, approximately 10 to the power of 20 kilograms of rock, soil, and water, distributed around the planet's midsection. Relaxation to a spherical geoid is viscoelastic and patchy. The timescale spans thousands to millions of years, depending on the material properties of different crustal regions. Solid rock responds much more slowly than sedimentary layers. Ocean basins adjust differently than continental shelves, and areas with different geological compositions will reshape at varying rates. The physics underlying this change involves the interplay between gravitational potential energy and elastic deformation. Currently, centrifugal force reduces the effective gravitational acceleration at the equator by about 0.5% compared to the poles. Without rotation, this support disappears, and the excess equatorial mass becomes gravitationally unstable. The equatorial regions would begin subsiding under their own weight, while mass redistribution would cause the polar regions to rise, following the principle of isostatic adjustment, similar to post-glacial rebound, but on a planetary scale. This process would cause massive earthquakes and potentially increase volcanic activity as the crust adjusts to new stress patterns. The subsidence of equatorial regions would create extensional stress fields, potentially opening new rift valleys and fault systems. Conversely, the rise of polar regions would generate compressional stresses, possibly triggering thrust faulting and mountain building. Existing fault systems would experience unprecedented stress changes, with some becoming more active while others might stabilize. The redistribution would follow predictable patterns based on current topography and geology. Areas with thick sedimentary basins, like the Gulf of Mexico or North Sea, would experience more dramatic subsidence than regions built on solid crystalline bedrock. Mountain ranges near the equator, such as the Andes or East African rift volcanoes, would experience complex adjustments as both the underlying crust subsides and the mountains themselves respond to changed stress fields. Sea levels would change dramatically through this reshaping process. Equatorial oceans would become shallower as the seafloor rises relative to the new spherical reference, while polar regions would be covered by deeper water as these areas subside relative to their current positions. The Arctic Ocean, currently averaging 1,038 meters deep, could become significantly deeper. Conversely, equatorial regions of the Pacific, Atlantic, and Indian Oceans would experience relative sea level drop as the ocean basins shallow. The total change in radius could reach up to 21 kilometers difference between the current oblate shape and the future spherical configuration. This would completely redraw the world map over geological timescales, with new islands emerging in current equatorial ocean basins, while polar land masses disappear beneath rising seas. The timeline for these changes would vary dramatically by location and geological setting, with oceanic crust adjusting over thousands of years, while continental crust could take millions of years to reach equilibrium. Most Earth life depends on the 24-hour circadian rhythm established by our rotating planet, a biological clock that evolved over billions of years and is now encoded in the DNA of virtually every living organism. These internal timekeepers are controlled by molecular mechanisms involving clock genes like period, cryptochrome, and clock, which create protein oscillations that regulate cellular processes with remarkable precision. Plants use this cycle for photosynthesis, opening and closing their stomata, timing nectar production, and coordinating flowering with optimal pollinator activity. Animals rely on circadian rhythms for sleep-wake cycles, hormone production, feeding behavior, migration timing, and reproductive cycles. With permanent day or night regions, ecosystems would face unprecedented evolutionary challenges. Current plant communities are finely tuned to daily light-dark cycles, with many species using specific photoperiods as triggers for seasonal behaviors. Day-neutral plants, which flower regardless of day length, would have advantages over short-day plants, which require long nights to flower, and long-day plants, which need extended daylight. C4 and CAM photosynthesis plants, already adapted to hot, arid conditions, would likely outcompete C3 plants in the continuously heated dayside regions. Plants on the dayside would need to adapt to continuous photosynthesis and severe heat stress. Constant photosynthesis could lead to photoinhibition, damage to photosystem II from excessive light energy, requiring enhanced protective mechanisms like increased carotenoid production and more efficient heat dissipation. Desert-adapted species like cacti, succulents, and drought-resistant shrubs would have significant advantages. Trees would face particular challenges, as continuous transpiration could lead to water stress and hydraulic failure in their vascular systems. Plants on the night side would need alternative energy sources or extended dormancy capabilities. Some might develop enhanced chemosynthetic capabilities, similar to deep-sea organisms that derive energy from chemical reactions rather than photosynthesis. Others could enter cryptobiotic states, suspended animation conditions already observed in tardigrades, certain seeds, and desert plants during extreme drought. Underground. Root systems and stored energy reserves would become crucial for survival during the extended dark periods. Polar-style adaptations to long photoperiods foreshadow potential winners in the twilight belt. Arctic willows, which currently handle months of continuous daylight, demonstrate how some plants might adapt. Similarly, animals like Arctic foxes, caribou, and polar bears already possess physiological mechanisms to handle extreme photoperiods, including modified melatonin production and flexible sleep patterns. These polar species could serve as evolutionary templates for twilight zone adaptation. The terminator zone would likely become a refuge for many species, creating intense new evolutionary pressures as biodiversity concentrates in this narrow habitable band. This zone might span only 1,000 to 2,000 kilometers in width, forcing the entire planet's terrestrial biodiversity into an area smaller than many current countries. Competition for resources would intensify dramatically, likely driving rapid evolutionary changes and potentially numerous extinctions as species compete for limited space and resources. Migration patterns would be completely disrupted as animals attempt to find suitable temperature zones, with current migrations replaced by a one-time migration toward the terminator zone. Marine ecosystems would face equally severe disruption, with phytoplankton productivity potentially collapsing in both permanently dark and excessively heated regions. The combination of extreme heating on the day side and reduced magnetic field protection could lead to partial atmospheric loss over time through several interconnected mechanisms. Earth's current atmosphere contains approximately 5.15 times 10 to the power of 18 kilograms of gas, with nitrogen, 78%, and oxygen, 21% making up the vast majority. Photolysis of water vapor on the day side could enhance hydrogen escape. The long-term outcome depends critically on magnetospheric shielding and upper atmosphere temperature dynamics that would be fundamentally altered in a non-rotating world. Water vapor in the hot dayside atmosphere could be broken down by solar UV radiation into hydrogen and oxygen through photodissociation. This process occurs when ultraviolet photons with wavelengths shorter than 240 nanometers strike water molecules, providing enough energy, 5.1 electron volts, to break the molecular bonds. The light hydrogen atoms, with their low atomic mass, would have sufficient thermal velocity to escape Earth's gravitational well, particularly in the heated upper atmosphere where temperatures could exceed 2000 Kelvin. Oxygen atoms, being 16 times heavier, would largely remain bound by gravity. This process, called atmospheric escape, has been observed on other planets with different outcomes. Mars lost most of its atmosphere over billions of years after its magnetic field weakened, and its gravity proved insufficient to retain gases heated by solar radiation. Venus, despite having Earth-like gravity, experiences ongoing hydrogen loss at rates of approximately 2 × 10⁶ atoms per square centimeter per second due to its proximity to the Sun and lack of magnetic protection. However, Earth's gravity, 9.8 meters per second squared, and likely residual magnetism mean partial, not runaway, loss would occur. The escape rate would follow established atmospheric physics principles. Thermal escape occurs when gas molecules in the upper atmosphere gain sufficient kinetic energy to exceed the escape velocity of 11.2 kilometers per second. For hydrogen at exospheric temperatures of 1500 to 2000 Kelvin, a significant fraction of atoms would achieve these velocities. More efficient escape mechanisms include charge exchange, where solar wind protons pick up electrons from atmospheric atoms, and polar wind escape, where ions follow magnetic field lines into space. The rate of loss would depend on the strength of the remaining magnetic field and the extent of dayside heating. Current models suggest Earth loses about 3 kilograms of hydrogen and 50 grams of helium per second naturally. In a non-rotating scenario with weakened magnetic protection and enhanced heating, hydrogen loss rates could increase by orders of magnitude, potentially reaching 100 to 1000 times current levels. Over millions of years, this could remove significant quantities of atmospheric hydrogen. Atmospheric composition would evolve in complex ways. The preferential loss of hydrogen would gradually reduce water vapor content in the upper atmosphere, potentially leading to a drier stratosphere. This would affect ozone chemistry, as water vapor plays crucial roles in ozone formation and destruction cycles. Carbon dioxide levels would also change through altered carbonate-silicate cycling, with competing effects that could lead to either CO2 depletion or accumulation. Over millions of years, Earth could lose a significant portion of its atmosphere, fundamentally changing surface pressure and further affecting climate and habitability, with surface pressure potentially dropping 10 to 20% over geological timescales. Without rotation-driven currents, ocean circulation would be powered primarily by temperature and salinity differences, a process called thermohaline circulation that currently operates as a secondary driver alongside wind-driven surface currents. Dense cold water from the night side would sink and flow toward the day side along the ocean floor, while warm, less dense water from the day side would flow toward the night side at the surface. This represents a fundamental shift from the current system where wind stress and Coriolis effects dominate surface circulation patterns. The current global ocean circulation involves multiple interconnected systems. Wind-driven surface currents, powered by trade winds and westerlies, create the major gyres, the North Atlantic subtropical gyre, the Antarctic circumpolar current, and similar systems in each ocean basin. These surface currents transport approximately 30 million cubic meters of water per second in major systems like the Gulf Stream. Beneath this surface layer, thermohaline circulation already operates as the global conveyor belt, moving water masses based on density differences created by temperature and salinity variations. Surface flow from day to night and deep return flow from night to day would create a dramatically simplified circulation pattern, with intense upwelling near the terminator zones. The physics driving this new system would follow basic fluid dynamics principles. On the day side, intense solar heating would warm surface waters and increase evaporation, creating both thermal expansion and increased salinity in remaining water. On the night side, radiative cooling would decrease water temperature and density, while reduced evaporation would maintain lower salinity levels. This would create a global conveyor belt circulation, but much simpler than current patterns that involve complex interactions between multiple water masses. Currently, the global thermohaline circulation involves distinct water masses like North Atlantic deep water, Antarctic bottom water, and various intermediate waters, each with specific temperature and salinity characteristics. The new system would be dominated by just two primary water masses, warm, saline dayside water and cold, less saline nightside water. The lack of Coriolis effect would eliminate the formation of ocean gyres entirely. Current gyres depend on the balance between pressure gradient forces and Coriolis acceleration to maintain their circular flow patterns. Without this balance, water would flow directly from high pressure to low pressure regions, creating linear flow patterns rather than the spiral currents that characterize modern oceans. Major current systems would disappear with profound consequences. The Gulf Stream system, which transports heat equivalent to 1 million nuclear power plants from the tropics to the North Atlantic, would shut down completely. The Kuroshio Current in the Pacific, the Brazil Current in the South Atlantic, and the East Australian Current would all cease. Upwelling and downwelling patterns would concentrate along the day-night boundary zones, potentially creating unique marine ecosystems in these regions. The new terminator zone upwelling would be fundamentally different, driven by the convergence of warm dayside surface water with cold nightside surface water, creating convective mixing that brings deep water to the surface. The timeline for these circulation changes would vary by depth and location. Surface currents would adjust within months to years as wind patterns change and thermal gradients establish. Deep water circulation would reorganize over decades to centuries as the ocean's circulation engine completely rebuilds itself around temperature and salinity gradients alone. Without planetary rotation, tidal bulges would no longer sweep around the globe daily, fundamentally altering one of the most predictable natural phenomena on Earth. Instead, they would track the Moon's approximately 27.3-day orbit, shifting coastal high-low patterns on a monthly rhythm modulated by basin shape and local bathymetry. This represents a complete transformation from the current system, where tidal prediction is precise enough to calculate high and low tides decades in advance. Currently, Earth's rotation creates the familiar twice-daily tidal cycle experienced at most coastal locations. The Moon's gravity creates two tidal bulges, one on the side, facing the Moon due to stronger gravitational pull, and another on the opposite side due to weaker pull, allowing the solid Earth to be pulled away from the water. As Earth rotates beneath these relatively stationary bulges, most locations experience two high tides and two low tides every 24 hours and 50 minutes, the lunar day. Global tidal ranges vary dramatically, from minimal changes in enclosed seas like the Mediterranean to extreme ranges exceeding 16 meters in the Bay of Fundy. The Moon would still orbit Earth every 27.3 days, so the tidal bulges would slowly rotate around the planet following this orbital period, but individual locations would experience much longer tidal cycles. The physics underlying this change involves the Moon's gravitational field interacting with a stationary Earth rather than a rotating one. As the Moon orbits, coastal areas would cycle through high and low tidal states over approximately 13.65 days, half the lunar orbital period, rather than 12.4 hours. Coastal areas would experience fundamentally different tidal rhythms based on their position relative to the slowly moving tidal bulge patterns. Tidal ranges could be more extreme in some areas, since the water wouldn't be constantly redistributed by rotation. Currently, Earth's rotation spreads tidal forces across the entire planet, creating relatively moderate tidal ranges at most locations. Without this distribution effect, tidal energy would concentrate more directly under the Moon's gravitational influence. Funnel-shaped bays and estuaries, which already amplify tidal ranges through resonance effects, might experience even more extreme variations as tidal energy becomes less diffused. The Sun's gravitational influence would create additional complexity in this system. Solar tides, currently responsible for the spring-neap tidal cycle, would interact with lunar tides in new ways. When the sun and moon align, spring tide conditions, the combined gravitational effects could create more pronounced high and low zones. During neap tide conditions, when the sun and moon are at right angles, the tidal patterns would become more complex with intermediate zones of varying water levels. Ocean basin geometry would play a crucial role in determining local tidal effects. Large ocean basins like the Pacific would respond differently than smaller enclosed seas. Narrow passages like the English Channel or Bering Strait could experience extreme tidal flows as water moves between basins with different tidal phases. These changes would dramatically affect coastal ecosystems adapted to current tidal rhythms. Intertidal organisms like barnacles, mussels, and seaweeds have evolved life cycles precisely tuned to twice-daily exposure and submersion cycles. The transition to this new tidal system would occur relatively quickly, with new patterns establishing within months as ocean basins adjust to the altered gravitational forcing. Human civilization would need to relocate to the terminator zone, the boundary between permanent day and night, where temperatures remain habitable. A 1,000 to 2,000 kilometre global band totals approximately 40 to 80 million square kilometres, 8 to 16% of Earth's surface. With only approximately 29% land globally, usable land area is a fraction of that. The exact width would depend on atmospheric circulation patterns, local geography, and the efficiency of heat transport between the day and night sides. Mountain ranges, large water bodies, and prevailing wind patterns would all influence where habitable temperatures could be maintained. Within this zone, temperatures might range from 0 degrees Celsius to 30 degrees Celsius, allowing for agriculture and human habitation with appropriate technology. The terminator zone would experience perpetual twilight conditions, with the sun remaining near the horizon and providing oblique lighting throughout the year. This creates unique challenges for agriculture, as crops would need to adapt to constant low-angle sunlight, rather than the direct overhead illumination most plants evolved to utilize. Greenhouse agriculture with artificial lighting would likely become essential for food security. Fixed cities could use underground or insulated habitats and controlled spectrum lighting to create stable living environments. Underground construction would provide natural insulation from surface temperature fluctuations and protection from the extreme weather systems that would develop along the day-night boundary. These subterranean cities would require sophisticated ventilation systems, geothermal energy sources, and artificial lighting systems that could simulate natural day-night cycles for human psychological well-being. The engineering challenges would be enormous. Cities would need to be essentially climate-controlled environments, capable of supporting millions of people. Energy requirements would include heating, cooling, lighting, air circulation, water purification, and waste processing, all while potentially dealing with limited surface access. Geothermal energy would become crucial, as solar panels would receive only oblique light, and wind patterns might be unpredictable due to the massive atmospheric circulation changes. Mobile populations could track the moving terminator annually, following the habitable zone as it shifts westward. The zone would move at approximately 0.986 degrees per day, or about 110 kilometers daily at the equator. This creates the possibility of nomadic civilizations that migrate continuously to stay within optimal temperature ranges. Such populations would need mobile infrastructure, portable housing, transportation systems, and agricultural methods adapted to constant relocation. The annual migration would cover approximately 40,000 kilometers at the equator, equivalent to circumnavigating the planet. Existing transportation infrastructure would be inadequate for such massive population movements, necessitating entirely new logistical systems. Resource distribution would become a critical challenge, as the terminator zone would need to support over 8 billion people within perhaps 5 to 10% of Earth's total land area. Food production would require revolutionary changes in agriculture, with vertical farming, hydroponics, and genetically modified crops adapted to constant twilight conditions becoming necessary. Social and political structures would face unprecedented strain as current national boundaries become meaningless, and new forms of governance emerge to manage either mobile populations or coordinate massive underground cities. The transition period would be the most critical, requiring unprecedented international cooperation and technological development to relocate billions of people before temperature extremes become lethal. The change from an oblate to spherical Earth would trigger massive geological activity as the planet's shape adjusts to the absence of rotational forces. Currently, Earth's oblate form creates a 21-kilometer difference in radius between the equatorial bulge and polar flattening, representing an enormous redistribution of mass that has been stable for billions of years. Stresses from mass redistribution of both water and lithosphere would drive earthquakes and volcanism, akin to global-scale glacial isostatic adjustment, but with forces orders of magnitude larger. As the equatorial bulge subsides and polar regions rise, the shifting mass would create enormous stress on tectonic plates through several mechanisms. The equatorial subsidence would generate extensional forces, potentially opening new rift valleys and normal fault systems around the planet's midsection. Regions like East Africa's Rift Valley, already under extensional stress, could experience accelerated rifting and increased volcanic activity. The Andes Mountains, sitting near the equator, would face unique challenges as the underlying crust subsides, while the mountain chain itself responds to changed stress fields. Conversely, polar regions would experience compressional forces as they rise relative to the new spherical configuration. This could trigger reverse faulting, thrust systems, and mountain-building episodes in currently stable regions like northern Canada, Greenland, and Antarctica. The stress patterns would be unlike anything in Earth's geological history, creating hybrid extensional compressional zones that don't exist under current tectonic regimes. Increased earthquake activity would follow predictable patterns based on crustal structure and existing fault systems. The Pacific Ring of Fire, already seismically active, would experience additional stress as ocean basins reshape and tectonic plate boundaries adjust to new force distributions. Transformed faults like the San Andreas system could experience changes in slip rates and earthquake magnitudes as regional stress fields rotate and intensify. Volcanic eruptions would increase through multiple pathways. Crustal extension in equatorial regions would provide new pathways for magma ascent, potentially creating volcanic fields in previously stable areas. The decompression of crustal rocks as surface loads redistribute could trigger partial melting in the upper mantle, similar to how Iceland experiences volcanism due to decompression melting beneath the spreading ridge. Additionally, the flexural stresses on existing magma chambers could destabilize them, triggering eruptions at volcanoes worldwide. The redistribution of ocean mass would add additional pressure changes to the crust through hydroisostatic effects. As equatorial oceans shallow and polar seas deepen, the changing water loads would create additional flexural stresses in ocean basins. Oceanic crust, being thinner and more flexible than continental crust, would respond more rapidly to these pressure changes. Mid-ocean ridges might experience changes in spreading rates as the stress fields affecting them shift. The process would be similar to post-glacial rebound, but on a global scale and with much larger mass movements involved. Currently, regions like Scandinavia and northern Canada are still rising at rates of several centimeters per year, thousands of years after ice sheet removal. The planetary shape adjustment would involve mass redistribution equivalent to thousands of ice sheets, simultaneously loading and unloading different regions. These geological adjustments would occur over thousands to millions of years, continuously reshaping the planet's surface through episodic and gradual processes, with different crustal types responding at different rates. The cumulative effect would be one of the most dramatic geological reorganizations in Earth's history. Over geological timescales spanning millions to billions of years, a non-rotating Earth would evolve into a fundamentally different planet. Earth would resemble a tidally locked exoplanet analog, permanent day and night sides, strong day-night circulation, and a narrow, habitable ring circling the terminator zone. This transformation would place our planet in a category similar to many exoplanets discovered around red dwarf stars, which represent roughly 75% of all stars in our galaxy and often host tidally locked worlds. The simplified atmospheric circulation would establish a permanent two-cell convection system, with heated air rising on the day side, flowing toward the night side at high altitude, cooling and descending on the night side, then returning to the day side at low altitude. This circulation would be far more stable and predictable than Earth's current complex weather systems, but also more extreme. Wind speeds in this global circulation could reach several hundred kilometers per hour as the atmosphere continuously transports heat from day to night sides. Extreme temperature zones would become more pronounced over time as atmospheric and oceanic heat transport reaches equilibrium. The day side could stabilize at temperatures ranging from 60 to 80 degrees Celsius in most areas, with hotspots near the subsolar point potentially reaching 100 degrees Celsius or higher. The night side would cool to -60 to -100 degrees Celsius, with the coldest regions at the antisolar point potentially approaching absolute zero in the absence of atmospheric greenhouse effects. These temperature extremes would exceed those found on any planet in our solar system except Venus and the outer ice giants. Gradual atmospheric loss would create conditions unlike anywhere else in our solar system through several long-term processes. Enhanced atmospheric escape, weakened magnetic field protection, and continuous photodissociation of water vapor would slowly strip away Earth's atmosphere over tens to hundreds of millions of years. The planet might eventually possess an atmosphere only 50 to 70% as dense as today's, fundamentally altering surface pressure, weather patterns, and the ability to retain liquid water. Life would need to evolve entirely new survival strategies, or concentrate in underground environments where geothermal energy provides stable conditions. Deep subsurface ecosystems, similar to those already discovered in South African gold mines and deep ocean thermal vents, would likely become the primary refugees for complex life. These ecosystems derive energy from chemosynthesis rather than photosynthesis, using chemical reactions involving sulfur, methane, or hydrogen to power biological processes. Surface life in the Terminator Zone would face continuous evolutionary pressure to adapt to perpetual twilight conditions, constant moderate temperatures, and simplified weather patterns. The planet's comparison to known exoplanets provides perspective on this evolutionary pathway. Kepler 438b, Proxima Centauri b, and TRAPPIST-1e are examples of potentially tidally locked worlds in their stars' habitable zones. These planets likely experience permanent day-night divisions similar to what Earth would develop, with habitability potentially confined to Terminator regions where temperatures allow liquid water to exist. This scenario demonstrates how fundamental planetary rotation is to maintaining the diverse, dynamic environment that supports Earth's current biosphere. The transformation would be irreversible on human timescales. Once Earth's rotation stops and the new equilibrium establishes itself, restarting planetary rotation would require energy inputs comparable to the planet's original rotational energy, equivalent to millions of years of total human energy consumption. This makes our planet's current rotating state a precious and irreplaceable characteristic that enables the rich, dynamic biosphere we depend upon for survival.